Hi, I'm Rick Kitsis from Albert Einstein College of Medicine, and I'll be presenting a talk tomorrow entitled Understanding and Targeting Necrosis Signaling in the Heart. The syndrome that most relates to this in the heart is myocardial infarction, where cardiomyocyte death is one of the main events. And as you know, cardiologists have become much better at treating the acute effects of myocardial infarction with angioplasty and stenting. But there still is a lot of patients who go on to develop heart failure, and this has become a tremendous contribution to mortality in the United States, the heart failure that results from ischemic events in the past. And necrosis is the major form of cell death of heart muscle cells in the infarct itself. In the peri-infarct region, the cardiomyocytes die slightly later, but mainly by apoptosis. And so this said to us that understanding the relationships mechanistically and phenomenologically between cardiomyocyte apoptosis and necrosis is very important. So several years ago, we began to look at mechanistic connections between these two types of cell death. And after doing a number of different screens, we came upon the discovery that BAX, which is a protein that is critical in regulating apoptosis in all cell types, also regulates necrosis. And the interesting thing was it regulates necrosis by a completely distinct mechanism than how it regulates apoptosis. And so we've tried to enlarge and deepen our understanding of how BAX regulates necrosis. And in addition, we've begun to think about ways to actually target BAX pharmacologically with small molecules with an idea toward eventually maybe having a rational therapy to reduce the amount of heart damage during a heart attack. So what I'm going to talk about tomorrow are some of the mechanistic connections between necrosis and apoptosis in the heart. The major molecular difference when we looked at this 2 years ago was that a different form of BAX was capable of regulating necrosis than apoptosis. Specifically, BAX has to oligomerize in order to permeabilize the outer mitochondrial membrane in apoptosis. But in necrosis, a requirement for oligomerization doesn't exist. Even mutants of BAX that are unable to oligomerize will support necrosis. And what we've been thinking about most lately is why that is the case. And it turns out that non-oligomerizable forms of BAX drive a second process, which is mitochondrial fusion. And mitochondrial fusion is very important in predisposing cells to undergo necrosis. Now, the big question is, why would sending cells into an interconnected state, a fused state of mitochondria, why would that be something that would make them more likely to undergo necrosis? And there are several reasons why this may be true, but the one we focused in on is whether having so many fused mitochondria makes it difficult for mitochondria to maintain quality control. And quality control in mitochondria is normally maintained by getting rid of mitochondria that are damaged by mitophagy. And we believe that it may be the case that BAX not only is a cell death molecule, but it also may be a molecule that's involved in regulating how easily mitochondria are disposed of through mitophagy. So I'm going to talk about that tomorrow. In addition, we've tried to think about ways we could actually target BAX in a rational way. So using a combination of structural biology and chemical biology, we have screened some in silico libraries, found compounds that are likely to interact with certain surfaces of BAX that are critical in its conformational activation. Now, I should say the way BAX gets activated is by changing its shape conformationally. So we've gone about trying to find small molecules that would alter this conformational activation and to test whether they potentially might be altering cell death in cardiomyocytes. And we found a family of molecules that we call BAX activation inhibitors, or BAIs, that have the capability of preventing BAX from becoming activated. And I will show some data that in completely in vitro biochemical systems, cell-free systems that involve just liposomes that contain BAX, these molecules prevent BAX from permeabilizing the liposome to let out its contents much like Bax permeabilizes mitochondria to let out cytochrome C during cell death. And we've taken it one step further from the liposomes back to the organelle stage, and then from the organelle stage back to the cell. And we found that some members of this family will actually block cardiomyocyte death in response to very prolonged periods of hypoxia, up to 18 hours of hypoxia. So the purpose of this research is really both to understand how cell death is regulated, and these days it's really not enough just to study one form of cell death. It's important to understand how different forms of cell death interconnect with each other. And then the second important thing is the translational potential. Could any of these possibly be prototypes of small molecule drugs that could be developed for use in patients? So in summary, what my talk is about tomorrow is about the basic biology of cell death, how necrosis and apoptosis interconnect with each other and talk with each other, and how this might be used to potentially develop new therapies for myocardial infarction. If one were able to cause or make there be less cell death during a heart attack, there'd be less chance of the heart eventually failing and less chance of subsequent mortality, because it's very well established that the amount of heart damage that takes place in that first day during a heart attack is the major determinant of subsequent heart failure and mortality. In addition, it may not even be that necessary to limit all of the cell death, but even just slowing down the kinetics of the cell death may give patients more time to get to the hospital to undergo other therapies, such as angioplasty and stenting, that have very short or very small windows during which they're applicable. And if this could be extended, more patients could benefit from these therapies that already exist. So through this type of work, we hope that this will help to achieve the American Heart Association's goals of helping people live healthier lives free of cardiovascular disease and stroke.